Okay, so good afternoon, everyone. Welcome to my talk. This is Lin Chen from Zhejiang University, and the title of my talk is Approximating Partition in Near-Linear Time. This is a joint work with Lian, Mao, and Zhang from Zhejiang University. Okay, so let's start. We studied the classic subset sum problem. So in this problem, given is a multiset X of n positive integers and the target value T. And the goal is to find a subset Y of the multiset X such that the sum of all integers in Y is maximized, subject to that this sum is no more than some target value T. And specifically, if this target value T is exactly half of the sum of all input integers, then this special case is called partition. So both subset sum and its special case partition are well-known NP-hard problems. And we study approximation algorithms in this paper. So more specifically, we are studying polynomial time approximation schemes, which in terms of subset sum problem, we are looking for a subset Y whose sum is no more than T, and which is at least 1 minus epsilon fraction of the optimal objective. So the best known p-task for subset sum problem runs in n plus 1 over epsilon square time. And this is actually the best possible assuming the mean plus convolution conjecture. So as we see that the study of p-task for subset sum is almost closed. I mean, of course, one may still look for some logarithmic improvement, but no significant improvement is possible unless the mean plus convolution conjecture is overturned. The situation for partition is quite different. Indeed, so far the best known algorithm for partition runs in n plus 1 over epsilon to the power of 5 over 4 time. And the condition lower bound is linear in 1 over epsilon. And so the condition lower bound is based on strong exponential time hypothesis. So we can see that there is still a gap between the upper and lower bound. So here in this table, we simply summarize the upper and lower bounds on the running time of p-tasks for partition. And as we can see that the classic algorithm dates back to the 1980s, and yet the problem is still not closed. So it's the time to close it. Exactly. So in this paper, we close the gap by presenting a randomized linear time algorithm. And it is worth mentioning that in terms of the deterministic algorithm, the best known result is still n plus 1 over epsilon to the power of 5 over 4 by Deng, et al. And Wu and Chen independently. Okay, so now let's start with the technical part. So we will approximately compute S of X, which is a set of all subset sums. And then we will determine whether the target value T lies within this set. The whole computation will follow a general divide and conquer framework. So to describe the framework, let us first define the sum set of two sets A and B. So the sum set of A and B is defined as the sum of all possible pairs A and B. So using this definition, the set of all subset sums of X can actually be expressed as the sum set of n sets, x1 plus x2 plus etc. till xn. So now let us look at this tree. So every node in this tree actually represents a set. And each leaf at the bottom actually represents the set of a single input integer. And we shall perform a bottom-up computation. Starting from the leaf, we iteratively compute the sum set of two adjacent nodes. And so therefore, we can see that each node in the tree actually represents the set of all subset sums of its corresponding leaves. And the root of the whole tree is essentially S of x, which is what we need. So now we can see that the overall running time of this divide and conquer framework equals to the time of computing all subsets. And the best known algorithm for computing the subset of A and B is linear in the input size plus the output size. And because throughout this talk, we shall always assume the output size is larger, so we simply stick to the output size. So as we can see that if we just naively apply this sparse convolution algorithm and combined with a straightforward rounding, then the overall running time would be n over epsilon or 1 over epsilon squared, which is still too large. In a very recent work, Wu and Chen actually showed that this running time can be further reduced to 1 over epsilon to the power of 5 over 4 by further combining some number theoretic idea. So roughly speaking, so when we round the input integers, instead of rounding it to an arbitrary integer of value 1 over epsilon, we can strategically round it to some smooth integer with a lot of prime factors. And using this idea, they are able to bring down the running time of the whole divide and conquer framework. But unfortunately, this idea does not further lead to a linear time. So in this paper, we actually use a completely different approach. So we use additive combinatorics. So more specifically, we shall use this theorem of Semrady and Wu. The theorem, very roughly speaking, it says that, okay, so let's consider a sequence of integer sets where let's say U is their largest element. So what can we say about their subset? So, well, if their total cardinality is large, then their subset must contain a long arithmetic progression. And this theorem would actually allows us to claim some useful property in the subset of AIs without actually computing their subset. And this will be very useful in bringing down the running time. Before I proceed, I actually want to bring to your attention another relevant theorem, which is interestingly also by Semrady and Wu. So in another paper by Semrady and Wu, they proved that if an integer set S contains many distinct integers, then its subset sum, then all of its subset sums must form a long arithmetic progression. So this theorem, as you see that it appears to be more relevant to our problem. And actually, the prior two papers that obtain the running time of 1 over epsilon to the power of 5 over 4 are actually both utilizing this theorem implicitly. So here, by saying implicitly, I mean both papers are actually not using it directly, but they are actually using an algorithm called dense subset sum algorithm by Brinkman. And the dense subset sum algorithm actually utilizes this Semrady 2006 theorem. And therefore, both algorithms are actually implicitly using this Semrady 2006 theorem. But in this paper, we show that the Semrady 2005 theorem is perhaps a better fit tool in additive combinatorics. So as we will see that this theorem complements very well with sparse convolution. And to the best of our knowledge, this is also the first application of this Semrady 2005 theorem in developing algorithms for knapsack-related problems. Okay, so let us come back to our problem. So again, so recall that the sparse convolution algorithm can compute the subset in near linear time in the output size. So therefore, the overall running time of computing each level, say A1, A2 till AL, actually equals to the sum of their cardinalities. And our method is fairly simple. So if this sum of cardinality is small, then we just use sparse convolution. Otherwise, if the sum cardinality is large, then we claim that T can be approximately hit. So, and therefore we will not actually need to compute the sum set anymore. So now, as we can see, that the problem boils down to that if the sum cardinality of AIs is large, then T can be approximately hit. So this is what we want to prove. And of course, our tool is a corollary of the previous mentioned Semiratis theorem, which states that if the sum cardinality exceeds 1 over epsilon, then their sum set contains an arithmetic progression of length 1 over epsilon. And so towards a further analysis, let us, for simplicity, assume that the sum of maximal elements in each AI is of the same magnitude as T. So then an arithmetic progression of 1 over epsilon actually means that because the arithmetic progression contains 1 over epsilon terms, so we conclude that the step length of this AP is epsilon times T. And therefore, so if this AP happens to cover T, so that means if T lies between the first term and the last term of this AP, then we are done. T can be approximately hit. So the bad case happens if the T is very far away from the AP. To handle the bad case, our basic idea is actually to create an AP, or actually a collection of APs that can cover a wide range. So let us assume that the sum cardinality of AIs is very, very large, so that even with a quarter of the input sets, we can already guarantee the existence of long AP. And now, now this is the AP, and let us take an arbitrary integer x from the remaining sets. And if we simply add x to every term of this AP, then we actually obtain another AP, which is essentially the previous AP shifted rightward by the amount of x. And if x is not so large, then actually the two APs will overlap. And we can consider the union of these two APs. So of course, the union of two APs may no longer be an AP, but we can see that first, it covers a much wider range, and second, its two consecutive terms is still bounded by epsilon times T. So if the union of two APs cover T, our target, we are also done. So we can actually generalize this idea to create many APs such that their union covers a very wide range, say a quarter of the total sum and to 3/4 of the total sum. And if T lies within this large range, then we are done. And as we can see that the only problem is that what if T is super small or super large compared to the sum of all integers? In this case, we can actually use color coding. Very roughly speaking, color coding, this method can partition the input into disjoint groups such that with very high probability, each group will contribute a constant number of integers to the optimal solution. And by color coding, we can actually enforce this condition. So I'm not going to further expand on that. I want to remark that a very similar method has been used in an earlier paper by Brinkman on pseudo-polynomial time algorithm for subset sum. And we modified his method for the purpose of approximation. So I'm not going to explain further details, I'm just using this figure as a simple illustration of the overall techniques, and I have omitted several points, and if you have interest, you can refer to our paper. Now, as a final remark, I want to point out that our method also gives a near-linear p-task for a more general problem of weakly approximating subset sum. Where weakly approximating means that, so if we view subset sum as a knapsack problem, then weakly approximating simply means a p-task that relaxes the constraint by epsilon fraction. And this is actually more commonly known before as a p-task with resource augmentation. And our method can also produce a near-linear time p-task for weakly approximating subset sum. At the end, I want to mention some open problems. So our algorithm is randomized, and because it leverages tools like color coding, randomization seems inevitable. And the current best deterministic algorithm runs in 1/epsilon to the power of 5/4. So it is desirable to have a linear time deterministic algorithm, or at least if we can improve the factor 5/4. And another open problem, which is perhaps more important, is whether there actually exists an order of W time algorithm for subset sum, or even partition, and where here this W refers to the largest input integer. So along this line, the best known result is actually due to Brinkman, which gives an algorithm of order of T, where T is a target. And as you can see that there is still a large gap between the largest integer W and the target T. But nevertheless, so I'm happy to announce that very recently we are able to make progress in this direction by presenting an algorithm with an intermediate running time, which is square root of W times T. And our result seems to suggest that an algorithm of order of W is likely to exist. Okay, thank you very much.